So thank you for coming, everyone. Today's speaker is Professor Hironori Oya at Tokyo Institute of Technology, and he will speak about Wilson lines on the moduli space of G-local systems on a marked surface. Please welcome.
Thank you very much for the introduction, and thank you for inviting me to this nice seminar. So today I'd like to talk about the Wilson lines on the modular space of G-local systems on a marked surface. And this is a joint work with Tsukasa Ishibashi and Lin-Hui Shen. And this is these are reference of today's talk. Okay, let me begin with the introduction of this talk. Okay. First, let me fix some notation. G tilde, let G tilde be a connected, simply connected. Simple algebraic group. And if you have some questions, please feel free to ask at any time. And sorry, the size of the font is okay? Is it too small?
I think it's fine.
It's fine. Okay, thank you. Okay, let the tutor be connected, simply connected simple algebraic group, and for example, SL2, sorry, SLMC, and G be the corresponding adjoint group. So it means that it has a trivial center, adjoint group. Okay, and we fix some marked surface. So I mean, let sigma be a compact, oriented surface. And today we assume that we have a boundary. And inside this boundary, we fix some finite set. So this is usually called marked points. Okay, and so for example, so this kind of surface is the state surface. Okay, sigma, and these points are n. Okay, and we fixed them. Sorry, we clarify the assumption on the marked surface. So the pair of sigma and m is usually called the marked surface. So surface with marked point. And so first, each boundary component has at least one marked point. One marked point. Sorry. One marked point. And the set of marked point is non-empty.
This means you don't allow puncture?
Yes, yes. So, and this is an important point. So we don't allow the puncture. So in particular, thank you for the question, for the comment. In particular, we don't have punctures. Sorry. And our marked surface has an ideal triangulation. Okay. So ideal triangulation means the triangulation of the surface whose arc, the endpoint of the diagonal is contained in M. Okay. Okay. So this is our assumption on marked surface. Okay. And for this this kind of surface, Fock and Goncharov introduce the some modular space of G-local systems, which is an algebra geometric avatar of the Teichmüller spaces. So this is the modular space. Sorry, modular space of twisted G-local system. Sorry, G-tilde. Sorry, in this case, twisted G-tilde local systems with decoration. So with some data which is called a decoration. On or maybe I should write sigma m. Okay, and on the other hand, Goncharov and Shen introduced the usually written as a P modular space. So P is sigma, which is the modular space. So this is closely related to the A modular space, but this is the modular space of G-local systems. And on sigma with some data called pinning, which I will explain later. Okay, and this is the very important data in this theory. Okay, and these two modular space, the pair of this modular space is forms so-called cluster ensemble in the sense of Fock and Goncharov forms a cluster ensemble in the sense of Fock and Goncharov. So very roughly speaking, so these modular spaces are dual to each other in some sense. Okay, and the goal of this talk, of today's talk, is to formulate a class of morphisms written as GC and GC, which is the G tilde valued function on the A modular space or G-varied morphism on P modular space, which we call Wilson lines. So we in this paper we introduced in these papers we introduced this kind of morphism, and today I would like to explain the idea and the basic properties of Wilson lines. Okay, and explain their basic properties. And if time permits, I would like to talk about the application of these morphisms. Okay, and here I didn't mention any algebraic structure of these modular spaces, and in fact, so these modular spaces are defined as a stack, but here I wrote some cross. So, and it means that so indeed, so this is defined. This modular space is defined as a stack, but there exists some generic part or open part which has a structure of algebraic variety. Okay, and in fact, we to define the Wilson lines, we need to restrict ourselves to this part, and P. On the other hand, so in our settings, so PG sigma already has a structure of algebraic variety. So these are the morphisms of between the algebraic varieties. Okay. So this is today's goal, and the motivation. So let me make some comments on the motivation, my personal motivation. So in my mind. So, so Wilson lines give. So these are algebraic varieties. So we can consider the ring of regular function on these varieties, and if we so this is a morphism of the a morphism between the algebraic varieties. So we have we can obtain the algebra homomorphism from this the ring of regular functions on G tilde to the ring of regular functions on this modular space, or from OG to OP sigma, and this so this algebra is cross-related to the cluster algebra. And or maybe I should say upper cluster algebra. And this algebra is cross-related to the cross-related. It means sometimes this algebra has a structure of an upper cluster algebra, and this algebra has a structure of cluster Poisson algebra. Poisson algebra. So I would like to understand these algebras by using the terminology of the matrix coefficients on G. So, I mean, I'd like to, for example, or I hope that we can understand these algebras. So these interesting algebras. By means of the representation theory of G or G0. And so under more precisely, so understand means understand. For example, we would like to investigate the basis, for example, basis or generators of these algebras and so on. So cluster algebras are defined purely in an algebraic way. So to study these interesting cluster algebras, we would like to use the representation theory of G. So and we would like to we would like to prepare the tools for studying these things by using representation theory. And I hope that, or I'd like to understand the quantum analog of these algebras. So in terms of representation theory of quantum groups. So in fact, so we can, in fact, so these algebras are related to cluster algebras. So we can consider the quantization of these algebras. So quantization means that some non-commutative deformation, one-parameter deformation of these algebras. And indeed, we can define these kinds of algebras in purely algebraic way. So I mean that as a, for example, we can define the quantum analog of these algebras as an intersection of quantum torus. But I consider that this definition is how to too algebraic to study these objects. So to understand or to study these quantized object in terms of representation theory, we consider that we need to introduce this kind of morphisms. But this is an ongoing work. Sorry, so in the quantum case, so we would like to study these algebras by means of the representation theory of quantum groups. So we would like to understand these algebras in more representation theoretic way. But this is the hope of this this project. So I consider that or I regard today's content is the first step to achieve these kinds of results. Okay, and so this direction is the ongoing work. Okay, but anyway, so today I don't talk much about the quantum analog, but today in the classical setting, so I would like to talk about, I would like to explain the Wilson lines. Okay, and in fact, the story for A and P are in some sense quite parallel. So today I'd like to focus on the P case. So in fact, so in the for A modular space, we need to consider some technical things. So to explain the idea of the Wilson lines, today we would like to focus on this part. We mainly focus on this part. And the Wilson lines for a P modular space is discussed in our first paper. Okay. So today. Okay, so this is the introduction of my talk. Okay, let's move on to the next topic. So, to the definition of the Wilson lines. On PG sigma. Okay. So to explain the definition of the Wilson lines, let me introduce more notations. So, we take the Borel subgroup of our group, our algebraic group, and its unipotent radical. I think this is a standard notation. And by using these subgroups, we define the base affine space as the quotient space as G mod U plus. So this is usually called the base affine space. And we can define the Fock variety as G mod B plus. So this variety is usually called the Fock varieties. Okay, and we have a canonical projection from here to here. Okay, which is denoted by pi. Okay. And so to define, so first we need to explain this modular space. So, and to explain this modular space, we need to explain the pinning. We need to explain the pinning. So, what is pinning?
So here you're not using G tilde.
Yes, we are working on the adjoint group. Okay, but I think this is a bit technical point. So now I think the similar construction works for the simply connected type, but in my understanding, so for to equip the positive structure on this modular space, we assume this kind of condition.
Yeah, you only talk about the P moduli space.
Yes, yes.
Okay.
Yes. Okay. So let me explain the pinning. So let me begin with the easy lemma. It's easy but important lemma. So the set of pinning is defined in this way. So there, in fact, there are several definitions of several equivalent definitions of pinnings, but here we adopt this type of definition. Okay, so pinning is defined as a pair of the pair of an element of base affine space and flag variety such that they are in generic position. I mean that there exists the element of G such that GA, GB is equal to B plus and W0 B plus. Here, W0 is the longest element of the wide group of G. Okay. So in this case, we call we say that this pair is in generic position. So generic position. Okay, and this is the set of pinnings. And the statement of the lemma is we can consider the diagonal G action on this set. We can consider the diagonal G action on this set. Then this is the statement is this is free and transitive. I'm sorry, this part is a definition. Okay, so this is the proof of this lemma is not so difficult. It's an easy exercise, but this fact is quite important.
I have a question.
Yes.
So GA, GB equals B plus or U plus?
Oh, sorry. Thank you. Yes. Sorry. G pi A. Sorry. Thank you very much. G pi A.
Okay.
Pi is a projection. Okay. Thank you very much. Yes. Yes. Sorry, and I need to write plus in the bottom. Okay. Thank you very much. Okay. This is free and transitive. So. If we fix some point in the set of pinning, then as a G variety, so this this set is isomorphic to the group G itself, and we take the base point or distinguished point in this way. So this is the sorry. So this is, I think this is the typical choice of this distinguished point. Okay, and then so as a G variety, this is isomorphic to PG. So this is isomorphic to G. So I'm G max to G max P sum. Okay, because this action is free and transitive, and we introduce two notation, pi plus and pi minus. So we can define a morphism from PG to BG. In this way. So the pi plus maps AB to pi A. And pi minus is the second projection. I mean AB to B. Okay. So we can define this kind of morphisms. Okay. So this is the preparation. And then we can define the modular space. PG sigma. Okay. So first, we write the connected component of the boundary. We write the set of boundary intervals as B, as board B, and boundary intervals means the connected component of the boundary set minus the marked point. Okay, so I mean that if this is a boundary, and this is the marked point, then so these arcs are the elements of B. Okay, this is called a boundary interval. Okay, and we endow the orientation of of the boundary interval with the orientation, which is induced from the orientation of the boundary of the surface. And write an element of write the boundary interval as M plus E and M minus E. Here, M plus E is the initial point, of E, and M minus E is the terminal point. So we consider the orientation on the boundary interval. So we can define the initial point and terminal point. And by specifying the initial point and terminal point, we index the boundary interval. Okay. Okay. So this is a notation. Okay, and the definition. Let me write the definition of modular space. So PG sigma is the modular space of the data L and P E. Here, so L is the G-local system on the market surface, on the surface. I mean, the principal G bundle with flat connection. And PE is the flat section of the local system flat section of this bundle. So since this L is a principal G bundle, so we can associate, we can consider the associated bundle corresponding to the PG, and flat section of this one defined near E on the boundary, which satisfies some condition. So so pi E plus of PE is equal to pi minus E of PE prime for M plus E is equal to M minus E prime. And where? So what is pi plus E and pi minus E? So pi E plus minus E PE is defined as the pi L plus minus PE of ME plus minus. So here, PE of ME plus minus is a variation. Sorry. So PE is a flat section, so we can consider the variation of PE at ME plus minus. So PE is defined near this boundary interval, so we can consider the variation of ME plus minus, a variation of PE at ME plus minus. So this is an element of L cross PG at M plus minus E. And pi plus minus L is defined as by using the pi plus minus defined here. Okay, so this is LG of PG ME plus minus to LG of BG ME plus minus induced now from induced from pi plus minus. Okay. So this definition is due to Goncharov and Shen. Okay, and this is the P modular space introduced by Goncharov and Shen. And so, sorry, maybe I should write some picture for this. Sorry, for this condition. So here, so if this is the surface, and if we have a marked point, right, and the direction of, so this is the boundary. This is the boundary of the surface, and so this is the initial point of E prime, and this is the terminal point of E. So this boundary arc, sorry, this boundary interval is E prime, and this boundary interval is E. And if we have this kind of situation, then we have the compatibility at this point. We have some compatibility at this point. So this is the meaning of this condition. So here we have the flat section of this bundle near this this boundary, and we have sorry, this is the PE prime, and we have the first section PE first section of this bundle near around this boundary. So, and this condition means that we have some compatibility at this point. So if we if we restrict to ourselves to this part, so these two sections determine the same element if we reduce to BG. Okay, so this is the condition. This is the meaning of this condition. And in fact, so sorry, so this this modular space is rigorously defined as a stack. P G sigma is defined as quotient stack, some quotient. But I don't explain the detail of the this kind of stacky definition. So please refer to Goncharov Chen's paper or our first paper. So sorry, we wrote the stacky definition of this modular space. Okay. Anyway, we can define this kind of space, and that's it. Yes, and we would like to construct the Wilson lines on this. Wilson lines mean some G-varied morphism from this space to from this space to G. So we would like to construct the G-varied morphism on this modular space. But to explain the idea of the construction. So the explanation in the case that our surface is the polygon is already enough. So, and if we restrict ourselves to this surface, so many things simplified. So now I would like to explain the definition of Wilson line in this case. And here, so the decay is, sorry, and here decay is the keigon. I mean, the disk with k marked points on the boundary. So this one. So M1, M2, M3. No, sorry, MK. So this is this is a decay. Okay. So we focus on this case. Okay. So first, in this case, so we can describe this modular space very concretely, because in this case, only the trivial G-local system exists. So in this case, of course, the fundamental group of the disk is trivial. So only the trivial G-local system exists. So non-trivial G-local system doesn't appear. So in this case, this modular space parameterize this data. So the data of pinnings. So this is called the data of pinnings, and this is in this case. So this is just the modular space of the pinnings. So I mean, which satisfies this condition. So I mean, in this case, we can describe this space in this way. So as a pair of pinnings. The pair of pinnings. Sorry. The pair of pinnings which satisfies P. Sorry. 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 I forgot to introduce one notation. So, sorry. Let be. So we label the boundary intervals in this way, and EI is the boundary interval given in this way. So here, so this is E1, and this is E2, and so on. and the direction of the boundary is this one. Okay. Then sorry. So then this modular space is described in this way. So this is the the subset. Sorry. First, we consider the subset of the pair of the pinnings which satisfies P. P. P pi minus P E I is equal to pi plus P E I plus 1 for I from 1 to k. And here P E k plus 1 is defined as E1. So we consider it in a cyclic way. And so this corresponds to this condition, and we need to consider these things up to isomorphism. So we divide we consider the quotient of this set by the diagonal action of G. So diagonal action. But this is an still an algebraic variety because this is isomorphic to the product of G. Okay, and and this set is, or this variety is written as configuration conf k of PG. And we can describe this this variety we have an in this way. So we have an alternative description. So this is just a pair of this is the pair of the base of an element of base of Line space AG of K, and here AI is pi AI and pi of AI plus 1 is in the generic position. I mean, so is in PG for I is equal to 1 to K. Here, AK plus 1 is defined as A1. Okay, because so the pinning, the data of pinning is a pair of AI and BI, and we write this pair in this way, and the pinning on this boundary is the data of pinning on this boundary is written in this way. But this condition says that here phi of a minus 1 is equal to bi. So in this sense, this data is under this condition, this flag is defined from this data. So we can remove the data of flags. Then we can obtain this description. So this these data already determines the pinning. But to define the pinning, we need to assume some generic condition. Okay. So this is the alternative definition of PG of DK. So this is a very concrete object, and the fact proved by Shen. Okay. In that this is sorry, this is smooth or fine variety. Okay. Okay. And let me give some more concrete examples. So for example, if we consider the triangle, then this is isomorphic to, and sorry, this variety is written as conf k cross ag. Okay, and this is in fact isomorphic to Cartan subgroup crot times G E W0, and this is the double Brussels. Defined as the intersection of B plus and B minus W0, B minus. So this is the opposite word. Okay, and the correspondence is given by given as H G maps to U plus H W bar U plus and G W0 bar U plus. So this is this is a certain lift of the longest element. Okay. So this is another concrete example. So NPG for is isomorphic to not H times this is a double Brussels, again a double Brussels, and in general, so this is as a variety isomorphic to H to the K minus 2 times double both summation variety. So in the sense of Shen and Wen. And this is known as the smooth affine variety. Okay. So this is an example. And so I'd like to define the Wilson line. So this is the main core of this talk. So we define the Wilson lines on this space, this modular space. So in fact, the idea is not so difficult. And I think this is this idea is might be well known for topologists. So so we define the Wilson lines in this way. So first, we note that PG cross PG divided by the diagonal action of G is isomorphic to G as a variety. And the correspondence is given in this way. So the pair are represented by P1 and P2 is written in this way. So since PG is the is written, an element of PG is written as G times P standard uniquely. So by using this description, we define the morphism from here to G as G1 inverse times G2 and times W0. And so this is for technical reason. I will explain later. For technical reason, we add this part, but the important part is this part. So if we define the morphism in this way, so this is well defined. So it does not depend on the choice of the representative, and this is a well defined isomorphism between the varieties. Okay, and
but you have to choose
yes.
the W0 bar.
Yes, and yes. So this is W0 bar means thank you for your question. So W0 bar is defined as the explicit lift of the longest element. Lift means while group is defined. Sorry, as H. So while group is defined in this way. So we mean the explicit lift of this element. So here. Now we defined. So this is a bit technical, but here first we take the reduced word of W0, and and by looking at reduced word, we define this element in this way. And here S bar I is defined as the 0 minus 1, 1, 0. Phi I of 0 1 minus 1, 0. And phi I is the standard ISL2 triple. Okay, does it make sense?
And this doesn't depend on the choice of reduced word?
Yes, it doesn't depend on the choice of reduced code.
Okay.
Thank you for the question. Okay, and by this observation, we can define the G-varied morphism on this space as follows. So for EI and EJ, for two boundary intervals, we obtain we have a morphism written as G of EI to EJ from PGDK. We consider it as conf K of PG to G. Here, PE1, PEK to W of W of PEI and PEJ. So this this is a definition of the Wilson lines. So we pick up from here. From here, we pick up two pinnings and look at the difference. So yes, so this morphism calculates the difference between these two pinnings in some sense. So and by using this morphism, we define the Wilson line in this way. So first we we pick up two pinnings and look at the difference between these two. Then this gives a very defined morphism from here to G. Okay, so this is the called the Wilson line morphisms. Along EI to EJ. So this is the definition. Okay. And but I think I need to explain the meaning of this morphism. So what is the meaning? Geometric meaning of this morphism. And if we could understand the geometric meaning of this morphism, we can immediately generalize this construction to the arbitrary surface. So this is a geometric meaning. So now we are considering the disk with k marked points on the boundary. k marked points on the boundary, and we focus on two boundaries, namely EI and EJ. And here we have MI, MI plus 1, and MJ, and MJ plus 1. So what is the meaning of this morphism? So first, now we have the section defined near this boundary, and which is written as PE. But since P, the set of pinning is isomorphic to G as a G variety, so the element PE determines the local trivialization. Near EI. So in fact, in this case, in the disk case, the local system is already trivial, but it determines the local trivialization near EI. I mean that we can take the local trivialization, or maybe I should say the trivialization of the local system, which makes PE to P standard. Such that PE can be seen as P standard. So we can take this kind of local trivialization. And for generalization, I'm now using the general terminology. And since PE is the first flat section, we can consider the parallel transport of this section. I mean, we can extend the local trivialization. Sorry. We can extend the local trivialization along this path. From EI to EJ, and we bring this section to from here to here by the parallel transport, and then it determines the local trivialization near EJ. But by definition, the pinning is attached to this boundary. The pinning PEJ is attached to this boundary. Then but we already have a local trivialization determined from this one. So this PEJ is written as G dot P standard. And this, sorry, P standard. So this is the technical assumption, but W is the P standard. Then this is the Wilson line from EI to EJ. So if you look at this data, then we can obtain the Wilson line morphism. So this is the topological meaning of this, or geometric meaning of the Wilson lines. Okay. So let me explain the case. Of that the surface is general. So the the definition is parallel, but we need to introduce some terminology. So in the general case, we may have some some genus here, or some non-trivial topology. So if we have a hole here, then the parallel transport along this path and parallel transport along this path is different. So we need to, so Wilson line should be defined associated to some path, some explicit path from EI to EJ. But we are now considering the flat sections, so this path should be determined up to homotopy. So we define the terminology in this way. So an arc class in sigma is arc class is the isotopy class of a path from such that C0, so the initial point, and the terminal point is on the boundary interval. Okay. Then and in this case, so the arc class is written as the bracket C. Now, from E in to in out, E out. Okay. Then at least topologically, so what we need to do for the definition of Wilson line is now clear. So it is completely parallel to this definition. So for an arc class define Wilson line. Now we can define Wilson line from PG sigma to G. In the same way as in the case of the disk. So, I mean, we bring so so this is the E in, and if this is E out, then we fix an out class. Then by definition, we have the flat section around E in, and bring it to this part by a parallel transport. And compare it with E out. Sorry, this is E in. And take and consider the morphism W between these two. Okay. Sorry for time reasons. So I skipped the very detailed definition, but so this is the topological definition. But here I should remark that there is an algebraic definition, which is written in our paper, in our first paper, and we can define algebraic means algebra geometric definition, and we can know that that PG sigma to G is the morphism between algebraic variety. But to explain this algebraic definition, so we need to explain the Stucky definition of this modular space. So I skipped it in this talk. But this definition is how to say, in some sense, very the same as this topological definition. Okay, so in this way, we can define the morphism from this modular space to this space to G. Okay, and in the remaining time, I would like to some properties and application of Wilson lines. Okay. Okay. Let me mention some properties. So first one is a very natural property, so which is called a growing multiplicativity. So this is a not so surprising property. So if for sigma one. So in fact, this modulus we can consider the growing of the modular space, which is defined by Goncharov and Shen. So for sigma one, sigma two, and no. Oh, we for sorry. So if we have um, two surfaces, and this is boundary one and boundary two, then we can consider the growing of the surface. Sorry.
Just to have a quick announcement about the timing. I have
Yes.
time
Sorry. Yes.
until I have time until noon, which is about 30 minutes. For those in the audience who have to leave early, we will be uploading the video for this lecture, just to let you know. So, Hironori, you can take your time.
Okay. Maybe I need more 15 minutes.
Yeah, that's fine.
Yeah. Sorry.
Yeah.
Okay. Sorry. I'm very sorry. Okay. So sorry. My handwriting is quite bad. So if we have two surfaces with boundary, so we can consider the growing of this surface. And more precisely, if we have the marked point, marked surface of this form, then we can consider the growing of marked boundary in this way. So then associated to this growing, Goncharov Shen gives the growing morphism in this way. PG sigma 1 plus PG sigma 2 to PG sigma. Then and to define the growing map, the data of pinning is quite important. But anyway, we have this kind of morphism. Then, and sorry. Then it becomes a puncture. And if we have the arc cross C1 and C2, then we can consider the concatenation of the path. Then we have in this setting we have the Wilson line associated to this concatenated arc cross is equal to the C1 times the C2. So and so for this multiplicativity, so we add W0 here. So to obtain this this clear formula, we need to add this W0. If we add this W0 here, then we can bring this one from here to here, and so this one corresponds to Wilson line for this one times Wilson line associated to this one. So for this formula, we add this one. Okay, and so this is not a surprising result, but I think
for this gluing map Q,
yes,
to make sense, you have to allow punctures in the definition of the P moduli space.
Yes, sorry. So yeah, for the definition of P modular space, so sorry, we can define the P modular space we can define the P modular space also for puncture surface. Okay. And P modular space and Wilson lines. But here for simplicity, so I assume that our surface is our surface doesn't have punctures. But this is for simplicity. So to define the modular space or Wilson lines, we can admit punctures. But for the P modular spaces, P modular space for puncture surface, we need to add one more data in the definition. So data associated to the puncture. So for puncture surface, we have to take the flat section, which is defined around these punctures, and with some compatibility with monodromy. So yes. In this case, we need one more data, and for simplicity, I assume that our surface doesn't have the puncture. Sorry, thank you very much. And yeah, for the definition of the Wilson lines, the existence of the puncture doesn't matter. The same definition works. But the second property, so yes. So is defined. Sorry, is. We also have this property or this result. In fact, this the regular ring of regular functions on this modular space is generated by the image of the dual of Wilson line morphisms. So Wilson line morphism is a morphism from PG sigma to G. So associated to it, we have a morphism from the ring of regular function of G to OG sigma, and and images of images of the morphisms let's see if we consider the many Wilson lines. So enough. So this is our cross. Sorry, this description is not good. Is the morphisms. Yes, morphisms of yeah, these morphisms, and I mean here now we consider the Wilson line morphisms for various classes. Okay, I don't say that this is generated by the image of some single Wilson line morphisms, but if we consider various classes, then we can obtain enough elements of this ring, and this is sorry for this theorem. the condition the condition that we don't have puncture functors is essential. If if the surface doesn't have a puncture, then this ring of regular function is generated by the images of the Wilson lines. A very brief sketch is if we consider the many Wilson lines, if we consider sufficiently many R-crosses, then we can embed this modular space to the product of G as a cross subset. So if we don't have a puncture, then we can obtain the cross embedding in this way. So then so this is generated by the images of the Wilson lines. So this is a very brief sketch. But if we have a puncture, we cannot have this kind of embedding. So this theorem doesn't hold. Okay. And so in this sense, by using Wilson lines, we can obtain many regular functions on this modular space. Regular functions on this modular space. Okay. And let me make some comments on AG sigma case. So the definition of the Wilson lines is in fact completely parallel. But here we need to deal with the twisted G-local system. So we need to consider the G-local system on some punctured tangent space. So we need some technical modification. Okay, and the Wilson line is associated is associated with the framed arc cross, so-called framed arc cross. C from E in epsilon to E out epsilon. Here, E in, E out is the boundary interval, and epsilon and epsilon prime is plus minus, plus or minus. Okay. But yeah, by this technical modification, we can define the Wilson lines in the same way. Okay. And in this case, we also have the parallel theorem. So I mean that all of sorry, comment on a cross case. So Wilson lines is defined by looking at the difference between the two pinnings, and the pinning is defined as a pair of the pair of flags which is in generic position. So so the pair of flags which is in generic position is essential for the definition. And so for this to achieve this genericity, we need to consider the we need to focus on the generic part of the modular space in this case. So for by the definition of pinnings, so the genericity is how to say, in some sense automatic for the P modular space, but for A modular space, we need to add some condition on the choice of decoration. Okay, and but then we can define the Wilson line. Then this is generated by the image of Wilson lines morphisms and let me make one comment on the application of the Wilson line morphism. So this is the last statement. So if we have at least two mark points and G Schiller admits minuscule representation, then I don't mention the cluster structure on the ring of regular functions, but in this case, we can show that the ring of regular function is equal to cluster algebras and upper cluster algebras. So in this case, the cluster algebras, A equal U problems for cluster algebras is solved. So this is the sheet associated. Sorry, so this should be G2. seed associated to this modular space. And this is a cluster algebra. And this is upper cluster algebra. And then in this case, A equal U problem is affirmatively solved. And this condition, minuscule representation, means that this is not of type E8, F4, and G2. Okay. And the very brief proof, sketch of the proof is we can show that G first, we can show that the ring of regular function on this modular space is equal to upper cluster algebra by some geometric argument. And here we can show that this is the Wilson line morphism. And we can show that some generalized minors are mapped to Goncharov Shen's cluster variables. Up to frozen. We can show that this kind of things. And if G admits a minuscule representation, then this is a bit strange condition, but if G admits the minuscule representations, so generalized minors generate OG tilde. So we can show that A of SG tilde sigma contains set of generators. Of this one. And by the Laurent phenomenon, we can say that A equal U problem. We can solve the A equal U problem. Sorry. So this is a quick application of the Wilson line morphism. I'm very sorry for the time. So I stop here. Thank you very much.
Thank you very much for the very nice talk. Let me first stop recording.